Okay, good morning. Today is heating and cooling and hydro. But first, we have a special announcement. Peter?
Yep, great. All right, my name is Peter Worley. I'm part of a group on campus called Net Impact. We're focused on building sustainable leaders through a certificate program. This Wednesday, we're hosting a career kind of networking event for sustainability industry. So it's this Wednesday at 5 o'clock is check-in, and it goes to 5:15, and then 5:30 it'll start the event where different companies around the state of Ohio will come in and give the quick 5-minute pitch about what they're doing in industry to implement sustainability. And that will go on for about maybe an hour, and afterwards it gives you the opportunity to then network with those industry leaders and talk with them, maybe see if you might be able to pass on a resume, maybe not, if it's all up to you, or just talk about how you can implement sustainability in the industry. So I just want you guys to know that. It's at the Blackwell at the banquet hall.
Okay, thank you.
Thanks.
What time? That's Wednesday at
Wednesday, check-in's at 5.
5.
And then the event starts at 5.
All right, great. Thank you. I'm sure that's of interest. All right, so let us see where we left off. How's the UK doing so far? Transportation, car transportation, jet flights, and we piled on wind, solar, photovoltaic farm, and biomass. And right now, if they have no other sources of use, and if you're wildly optimistic about these sources of power, then they come out ahead. Ohio, we look even better. I estimated the same plane and car use, and we had a lot more potential for solar. Does anyone remember the reasons why? One reason was we have more area per person, and the other one was?
We have a little bit better sun.
Better sun, right. Okay. So, but a lot of energy is used to change the temperature of things. So we like to have hot water when we take a bath. We like to heat the air at home and at work. And we also like to cool stuff. So I have a frosty beverage here, and we like air conditioning. But saying a lot doesn't mean much. And as we know in this course, we want to put some numbers on that. So we're going to ask the question, how much is a lot? This is a little hard to get a handle on, so we're going to try it from a few different directions. First, let's consider if you take a bath. The volume of your bathtub might be 50 centimeters by 150 centimeters by 15 centimeters deep if you don't fill it all the way. That works out to about 110 liters of water. And maybe you like your bath at a scalding 120 degrees Fahrenheit. That's pretty hot. But let's say the temperature of the water coming into your house is actually about 10 degrees, depending, of course, on things, but that's about the temperature. So you have to change the temperature of that water, that 110 liters, by 40 degrees C to make a comfy bath. The heat capacity of water is 4,200 joules per liter per degree C. So the energy used to heat that water, here's the heat capacity in joules per liter per degree, times the number of liters, times the number of degrees, 18 megajoules, or 15 kilowatt hours of energy to heat your bath. Did I say 15? I meant 5 kilowatt hours every time you take a bath. Who takes a bath? Well, I think more people take showers. The industry standard for the United States anyway is 2.2 gallons per minute. I believe this is the United States number. And we can convert that to liters per minute here. More efficient shower heads might use 1.5 gallons per minute, and it's hard to find the old refreshing shower heads. Now we get the efficient ones, so maybe 1.5 gallons per minute. The average American takes about 8 minutes in the shower, and so that's result is 66 liters per shower times 1 shower a day. We'll just say 1 shower a day, unless you're an athlete, it might be more. And that requires about 3 kilowatt hours per day per person. Again, all the per person's things are deleted here. 3 kilowatt hours per day to heat your shower. Also, it's interesting that the average American uses 70 gallons of water per day, according to the this isn't the citation for, where's the citation? I think still these guys, some American Water Association. We use 70 gallons of water per day compared to the average European of about 50 gallons. So we are more energy intensive. Are we using that water for showers? Doesn't say. We just know that we're using it. Water use in the home. So this is from American Water Works Association. So these would be American numbers, I assume. Showers, gallons per capita, about 11.6. This is daily use. Clothes washers, averaged over the whole week, 15 gallons. Dishwashers, a gallon. Baths, 1.2 gallon. Toilets, 18 gallons. Wow. Leaks, wow, better fix that faucet. Faucets, other domestic uses. So if you look at the ones where we have to heat the water, it's these four that are circled, and somewhere here, oh, I bet when I press this button, it'll say about almost half of the water we use in our home is heated, not quite half. Also, on this side, notice this is liters per day per person of water used by people from all these countries. Here's Spain, Norway, Netherlands, France, Switzerland, Luxembourg, Austria, Hungary, Denmark, Germany, Poland, Slovenia, Belgium, Estonia, and Lithuania. Guess who's not on here? England. So we don't know how David McKay stacks up on here. Here's the USA at about 280. We actually use more water per person than even people in Spain. We'll just leave it at that. Maybe you like to cook your food or your drinks, so you like a nice hot cup of tea. In the UK, they have 220 volts, and if you have a 13 amp tea kettle thing or an electric heater like that, P equals VI, we know that. Power is equal to current times the voltage, so that works out to about 3 kilowatts to heat a cup of tea. For the United States, we're on 110 volts here. So we might have 15 amps. It takes us twice as long to boil water because we have lower voltage. So we might use 1.5 kilowatts, but we might be doing it for a longer period of time. Electric toaster might take a kilowatt. Microwave oven, if the microwave oven, by the way, says it's a 1 kilowatt oven, it's actually consuming 40% more than that. Just so we remember that there are conversion losses. If you have an electric oven, maybe that's 3 kilowatts. Washing dishes and clothes, your washer, dryer, dishwasher might be 2.5 kilowatts. Your washer uses maybe 20 gallons of water. And of course, your washing machine probably heats to 40 degrees. Dishwashers, I know, have a separate heater inside so that you can bring in hot water, but then they heat it up even hotter to sterilize your dishes. So that gets even hotter. This is at 40 degrees C, a kilowatt hour. Here's some typical numbers. This is from McKay, so these would be Cambridge numbers, presumably. Cooking kettle, 3 kilowatt hours. He's saying maybe he has that on 1/3 of an hour a day, so he's not drinking a lot of tea. 1 kilowatt hour per day. Microwave, so he adds up all these different numbers. Electric cooker, rings, I think he means a stove. I'm thinking. Electric oven, okay. Cleaning, so washing machine, the tumble dryer. Airing, cupboard drying. Does anyone know what that is? Huh, me either. I've never been to England. But it's less power than a tumble dryer, so maybe it's like a closet you put clothes in, then it's just warm in there. I have no idea. Washing line drying, yeah, 0, I would say. But I don't know if they have zoning laws there. Here, in a lot of neighborhoods, you're not allowed to hang up your clothes. Dishwasher, 2.5. Cooling, refrigerator. He's got 0.02 kilowatts, but it's on all the time, so that's a 0.5 kilowatt hour per day there. The freezer, 0.09, that's on 24 hours a day, 2.3 kilowatt hours per day per person there. Air conditioning, 0.6 kilowatts. He's got it on 1 hour a day for 0.6 kilowatt hours per day. Those are the British numbers. Hot air. In the United States, most houses, I think more than half, use gas to heat. But electricity is a little bit more familiar, so let's just look at it in terms of an electric heater as if we had that. So McKay says, what if you had a small electric heater, you put it near your desk, you sit near there, you wear a warm sweater, 1 kilowatt hour, so if you have it on all day, it's 24 kilowatt hours per day, at least in the winter. And that's if you move it around with you from room to room. Who does that? Well, most people heat the house or heat the apartment. So if you use it half a year, he's saying use 12 kilowatt hours per person, but really, we're usually heating multiple rooms. In my case, I'm heating my entire house, whether I'm home or not. So 24 kilowatt hours per day per person is pretty conservative for the UK. And don't forget that public buildings are heated on your behalf. So the Kroger's heated on your behalf, the gas station inside is heated, OSU Dries Lab is heated on your behalf. U.S. heating. So I got some statistics here from this. Actually, this came from a Texas site, but they had U.S. numbers too. 6.9 quadrillion BTUs. So here we got a unit problem again. To heat homes in 2005. So I converted that to 18 kilowatt hours per day per person. I think McKay thought 12, right? So this says 18 just to heat homes. Then we use another 4.1 quads. This is slang, quads BTUs, quadrillion British thermal units. How ironic, we have to convert those to kilowatt hours. To heat commercial buildings, so that comes out to another kilowatt hour per day per person. So I took this number, converted to kilowatt hours per day, divided by the number of people in the U.S. That's how I arrived at that. So right between those, there's 28. Hot water. The UK estimate was 12 kilowatt hours per day per person. The average American uses 70 gallons compared to Europe's 50 gallons. That was an average for Europe. So I just multiplied this 12K by this 70 to 50 ratio. That was the best way I could get at it. And I got 17 kilowatt hours per day per person, if you believe his numbers to start with, and you believe this method. So you get to evaluate the method yourself. For hot water. Cooking. In 2001, electricity used for stovetops, coffee makers, and oven was about 0.7 kilowatt hours per day per person, but many people use gas for stoves and ovens, so I rounded that up to 1. Okay. The total then for the U.S., based on this very loose system of estimating, because I didn't know how else to get at it, 46 kilowatt hours per day per person. Ohio is in the north of the U.S., so we may heat a little bit more average than the average for the country. Cold air. Oh, so I heat my house and then I refrigerate a small volume in the house to keep my milk cold. Fridge, 18 watts, about half a kilowatt hours per day per person. Air conditioning. Depends on climate. So here's England. Isn't this cute? 30 days a year they need air conditioning at 12 hours a day. That's not like here. Window-style air conditioner might use 600 watts. You multiply that 12 hours, you get 7.2 kilowatt hours. So he's saying average is 0.6 kilowatt hours per day. But we're not done. What about refrigerators and stores and food transport and all that stuff? We'll have to take that into account somewhere along the line. Total heating and cooling estimate for the UK. Heating and cooling, he gets a total of 37. I think we had 47 just for heating in the US. Very interesting. They use a lot more energy for travel than they do for heating and cooling. I'm not sure it's the same for the U.S. Let's take a look. Here I got some numbers for electrical power in the U.S. So 107 million U.S. households in 2001. That's the data I found. So many billion kilowatt hours. I came up with 1.1 terawatt hours. Then that worked out to 106 megawatt hours per household. 290 kilowatt hours per household per day. If you think there's 4 people in the average household, that may be a little optimistic. 72 kilowatt hours per day per person, electrical power. But this is electricity for all purposes. This site didn't specify heat or anything like that. And it doesn't include that most houses are heated by gas here, which does have a carbon impact. So we didn't, and I can't find any numbers to figure out how to get a good handle on that. And again, doesn't include public uses like air conditioning in the grocery store. Or those stupid freezers in the grocery store where they're open, you know, and you just reach in and they're freezing all that air and then it flows out and it's very lossy. So, let's take a poll. Which of these do you think consumes the most power in U.S. households on the average? How many people think we use most of our energy for cooking? Nobody thinks that because we all go to McDonald's. How many people think we use it for heating? Okay, 3 people say heating. How many people think it's cooling? We got another 3 for cooling. How many people think we use it for cleaning? It turns out it's cooling. We use more energy for cooling than we do for any of those other things. Here, thinking about how much air conditioning and heating the guy in England has to do, here are the January through December annual high and low temperatures by month for London, and here they are for Columbus, Ohio. So even if our average temperatures aren't that different, our extremes are much different. We get much colder in the winter And we get much hotter in the summer, which is probably why we're running our air conditioners more than 12 hours for 30 days. Here's Phoenix. Okay, Phoenix, so these balls actually have the temperatures in them. 31 is their, this is the record high, that bright red one. But their average high, and these are degrees Celsius, 19 Celsius, 27 Celsius is room temperature, to give you an idea. 42, that's hot. That is blistering hot. Here's the Columbus highs here, the London peaks here. Here's the low temperatures in Phoenix. So Phoenix is doing some cooling, some heating, but they're doing a lot of air conditioning. Here are winter average temperatures in 2009 for, what country is this? United States. And winter averages, so we're kind of this aqua color that's between 20 and 30. That sound about right? Where's Phoenix? It's Phoenix. This is Nevada. That's Nevada. This is
Arizona. Yep.
This is Arizona?
Yep.
What's this one? New Mexico. I get them mixed up. I can keep New Hampshire and Vermont straight. I can't keep these straight. So Phoenix is in Phoenix, Arizona. It's in this one. Yeah. So anyways, they're somewhere there in the 40s to 50s. Summer averages. Don't live in Phoenix. Columbus, we look like we're between 70, 80. Those are averages. Of course, we get peaks in the 90s. Occasionally we go over 100, not too bad. So there's a lot of regions here that are doing a lot of air conditioning. If only we could use that heat to store it until we needed it in winter. How was electricity used? Here is Department of Energy, so this is U.S. data here. The most significant end uses were central air conditioning, refrigerators, and freezers, and each of those accounted for 14% of the total. So let me read you these. This is air conditioning, this is 16, space heating, HVAC appliances, kitchen appliances. Why is this so high? Fridge, freezers, right. And this is electricity. I have a gas stove. That wouldn't even show up here. It's my refrigerator that's the problem. Water heating at 9, lighting. Wow. I'm surprised we use so much energy for lighting, almost as much as we do for heating water. Home electronics, so what's that? The TV, the phone charger, the computer, other equipment. I don't know what that is. Other end uses. I don't know what that is either. This plot says most of the household energy used in the USA in 2001, but I looked and it's actually electricity. So again, this does not include gas or anything else. This is just purely electricity. Electricity. U.S. total 356 kilowatt hours. Look, half of it is air conditioning. HVAC. Oh, this is just the HVAC stuff. Consumption 356, of which half is air conditioning. Some is space heating. This says furnace fans, and this says other HVAC. Kitchen appliances, refrigerators, clunk, half. Freezers, hunk, another hunk. And then a few heating things. Gadgets, color TVs, a third. Printers and PCs, another quarter. TV peripherals, another home electronics. Gives us an idea of where we're putting all this electricity. So I think it's fair to say that heating and cooling are significant consumers of energy. And when we think of heating and cooling, we usually think about air conditioning and space heat, but stoves and particularly refrigerators are a big contributor. 40 kilowatt hours per day per person, about as much as driving in the UK. I'm figuring 70 to 80 kilowatt hours per day in the US. You'll do the calculation for homework. Oh, you're going to do the calculation for cooling for homework, I believe. That reminds me. I delayed the home, so I got all confused about which homeworks were posted. Homework 2 was supposed to be due this Wednesday. We're moving it to next Wednesday. Homework 3 I posted, and it's really due February 6th. So there's no homework due this week, so everyone who has a midterm, you can say thank you. I heard people had midterms. All right, so looking back here, heating and cooling, let's look back here. Nope. Fine. Well, we need more energy anyways. So let's look at hydroelectric next. So for that you need water and you need elevation changes. So you need water to go from high places to low places and turn turbines or do something. Here is England. The estimate the amount of water, the energy of the water. So what he did was he added up all the rainfall, and then he estimates the energy it can produce as it runs down towards sea level. Gravity. We don't have to pay for gravity. That comes free with the planet. So the factors are the amount of rain, and the elevation difference. How far down can it go? So he divided UK into lowlands and highlands, and he came up with 2 estimates. Britain has sea all around it, so their water can flow directly to the ocean. In Ohio, it does not. Lowlands in the UK, so here's how he figured this. He said, let power be the mass of the water times gravity times the height, and the mass is the volume times the density. So he says, well, we get 600 millimeters per year, and here it's converting years to days, days to hours, hours to minutes, minutes to second, because he's got these things, gravity and stuff, in meters per second, so he needs this in seconds. 1,000 kilograms per meter squared, that is the density, thank you, I was trying to think of the word for water, and gravity, and then 100 meters is how far the water in the lowlands can go. And he gets about 0.02 watts per square meter. Then he multiplies that by the area of lowlands per person in England, and he gets about a kilowatt hour in the lowlands. Oh yeah, we have to point to all these things. Height. Okay, so in the uplands, they have about 4 times more rain and 3 times more altitude. Power of water comes up with this number, gets about 7 kilowatt hours per day per person in the UK. But that's optimistic because some of it's going to evaporate, some will be lost to other things. So maybe 20% of that is doable. Okay, so if you believe 20% of 7 kilowatt hours per day, you might get 1.5 kilowatt hours per day per person. What they're actually getting right now is 0.2. So they have some room potentially to put in some more hydroelectric plants and maybe squeeze out a little bit more energy. So how's that add up in the UK? 7 kilowatt hours is the max possible. At 20%, we're saying 1.5. But remember what they're actually doing is 0.2. But he's got the 1.5 up there. It's not helping a lot. So let's take another poll. What are the most important factors for hydroelectric power production in a region? How many people think it's altitude and the amount of water? How many people think it's the amount of water and the altitude variation? Right. Rainfall and soil type, no. Average temperatures and size of reservoirs, no. Amount of water and how much can it go from low to high? High to low, sorry, it goes that way. Hydroelectricity, the potential varies across the world. Some places have lots of potential, some people don't. Worldwide, hydroelectricity supplied nearly 3,000 terawatt hours in 2006. That was approximately 20% of the world's electricity. So some places are getting a significant fraction of their power from their energy from hydroelectric. US is getting about 7.7%, I think it is. And this accounted for about 88% of electricity from renewable resources. Wow, so if all the renewable resources in place right now, almost all of it is hydro. Here's the world's largest hydroelectric plants. Until 2009, the Itaipu power plant was the hugest one on the border between Brazil and Paraguay. Here it is. Don't go swimming there. Thing's huge, it's massive. But they have this giant river there. Does it say the river? I can't remember the name of the river. It's probably something like the Paraguay River. But anyways, it supplies 1 jillion megawatts. It's 26, almost a quarter, more than a quarter of the electrical power consumption of Brazil. Brazil's a huge country. And 3/4 of the power consumption of Paraguay. In Brazil, I'm thinking, well, they have a lot of sunshine, you know, they probably have wind, but no, they're getting a boatload of their energy from this one dam. This is the Three Gorges Dam in China. It's also huge, 21,000 megawatts. There's a Guri power plant in Venezuela, another 10,000 megawatts. Here's an interesting table that shows countries and how much hydro they have. So China, and I don't have a year on this one, so I don't know. Oh, this is a 2006, that's 2008, the rest I don't know where they come from. So China, 585 terawatt hours. Let's see if it says percent of all electricity is the last column, 17%. Canada gets 61% of their energy from hydro. That's pretty impressive. Brazil, 85%. United States, this says 5.7%, just a little bit different from another number I saw. Russia, Norway, I'm thinking very tall mountains and all their water can go to the sea, and I bet you they get a lot of snow. India, 15%. Venezuela, 67%. Japan, Sweden, Paraguay, numbers not shown, but we heard it was 75%, and France is 11%. And this is the map that says that we are using 7.1% conventional, hydroelectric conventional, as opposed to tides and things like that, which we'll get to. Oh, look, coal, natural gas, nuclear, 20% nuclear. So let's see what's our potential for hydro in the U.S. Let's see, where does it rain? Oh, it rains in these regions here. Oh, they're kind of flat. Rains in the Pacific Northwest. They got mountains there. So you can see these are the top hydro-producing states. What's magic about New York? It doesn't look like it's rainfall. Niagara Falls. New York does get some rain. But Niagara Falls is a huge deal, and I'm guessing that accounts for a lot of Canada's power too. But I don't know that for a fact. Washington, Oregon, they have the Columbia River and a lot of rain. So this is called a run-of-the-river dam, and we'll show it a little bit, where you put a dam in a river and you let the water go through the dam where the river already was and drive some turbines. As opposed to, and then there's also reservoirs producing dams where you can dam it up and let the power up when you want to. California also imports hydroelectric power from the Pacific Northwest. Montana kind of surprised me. I think of Montana as being pretty arid, but it looks like it's pretty moist over in these regions here. And I know the Rockies go right through here, so that may be why they have so much. Oh, here is High Head low power is orange. Existing hydroelectric plant is yellow. So High Head, low power, exclusion areas. These purple things are the places where you may not put hydro even if you want to. Things like national parks and stuff like that. Environmental avoidance, wildlife avoid. So you can't really see Ohio. I can see because I'm up close. There's one there, there's one there, there's one there. That might be one. Yeah, look, a couple down there. We don't have a lot. Niagara Falls. So here's a picture of the first major hydroelectric power in 1895, and Tesla invented the, who cares, but anyway, so he invented these generators basically, and they put, they used 13 of his patents that bought by Westinghouse. If you're ever interested in reading about the AC-DC wars, there's a couple of great books out. Edison was pushing DC and Tesla was pushing AC, and it looks like Tesla won. So here's a run-of-the-river plant. So this is not at the falls. All right, that's a common misconception. It's actually downriver of the falls, but the river still is running through there, and they collect energy. And let's take a look in the guts of this. Here is a tunnel while it was being built that goes under the city of Niagara, and give you an idea of the scale, right? Here's a turbine, here's steps, here's a railing. So a person is this tall, is very huge. And here's how hydroelectric generation works. So, for example, I think I'm going to use this because my arm's getting tired of reaching. Go back. Go forward. Here is a storage reservoir. You got a gate here. You let water come in. The water comes in. Gravity turns this turbine. The turbine over here, see the blades, rotates a rotor inside a stator. And those are coils of wire or something like that, and they generate electricity. Here's a person. I believe, this is coming up, polyphase AC generation. So polyphase, like we have three-phase power in our system here. Faraday's law of electromagnetic induction. Faraday's law says, among other things, if you take a magnet and you run it through a coil of wire, it will induce a current. I can prove it. I have here a piece of sewage pipe with wire wrapped around it, and I got a couple of magnets here. Whoops. Don't put the magnet near your pacemaker, your splash sticks, your parking pass, your credit cards. And don't let the magnet shoot out and hit somebody else in the head. So the same kind of principle here. They've got these rotors are rotating inside a magnetic coil, and they are inducing a current. Okay, so magnetic field variation between the coil and the magnets creates an electric current. That's what we're saying here. The rotor turns, the stator stays. Here is a three-phase generator. I hope. Oh. Please, please, please show us this nice video. So a loop of wire called the rotor represents a coil and an actual motor, and then they've got permanent magnets here, and they're going to rotate this thing. Can I, does this do this what I want? Start generator. All right, so here's a side view of the rotor, and as it rotates, we generate current, and it gets to this position, we go back to zero. It only works when it's moving. Let's play that one more time. Okay, single-phase generators are limited to applications that have small power demand. So that was a single-phase generator. But if you need more power, you can put 3 rotors in there. And here's a picture. So they got 3 different rotors, and each one is connected to a different system so that they each can generate electricity. Here's the 3 phases, and I think we have a nice animation here. Okay, and we're going to measure the output voltage. Here we go. You see that the 3 phases are out of phase by 120 degrees. And I don't know why it's 3. I think it's just magic. That's the one that you get the most net power out of. So this is the map of the red one as it turns. And while it's turning, the green one is also turning, but it's out of phase by 120 degrees. And the purple one also out of phase by 120 degrees. So then you're constantly generating electricity from all 3 phases. And that's what's transmitted in our power systems. Single-phase generators produce, what do you think? Less, more, or the same as 3-phase? Less. Oh, that's the end. That's the end of my quiz. All right, I guess we're done. Question 1 of 3. Oh, I have to choose one. I am correct. 3-phase generator produces AC voltages that are 120. Rotors of the generator are 60 physical, 120 electrical, or both? Oh yes, I meant to say. Okay, we're done. How do I quit this? Do I do this? Great. Speaking of generators, I have, well, I don't know which one to show you first. This one's not a generator. This is a motor. Here I have a coil of wire. Oops, I can't stroll out of the view of the distance, guys. Here I have a coil of wire. Actually, maybe I can show this on a document camera. And maybe I can't. Left projector, document camera. Did I get the right one? No. I don't know if it can see this or not. Oh, okay. Here is a magnet, and this is just 2 metal hooks here, and there's a battery hooked up. And this rotor is a coil of wire, and I scraped, not me, somebody, scraped the insulation off of one side of the rotor and not the other side. So when it's hanging this way, current can conduct, and when you run current through a coil, it creates a magnetic field. That magnetic field is going to push off this permanent magnet down here and rotate this. When it turns over, if the current kept flowing, it would try to flip back again. But since I have the insulation on there, it'll just shut off. Momentum will keep it going. And voila. There's a motor. If instead I had a little crank here and I could turn this rotor, I would generate electricity and put it back into the batteries. And that's how a turbine works. I have a couple of generators here. When you crank that, you're turning a magnet inside a coil, and you might have to push the button because there's different settings for on and off. Polycom. You said 7, that's not the one I want. 5, that's not the one I want. 4, there we go. We're seeing people cranking these flashlights. So you notice when you crank that, you can feel resistance. So is that just because it's badly made and it's friction? No, you're putting energy in to try to light up that light. So you're actually feeling the interaction of the magnetic and the electric field. Okay, everyone's done having fun with that? I will tell you a story as soon as I figure out which preset I like here. That's not the one. 4, that's not the one. 3, I could look it up, but it's so much more fun to guess. 5, and a much better use of your time. 7, all right, 7. I teach a photonics lab, and people always need to have the lights off so that they can take their measurements. So I used to buy regular flashlights so people could find things in the cabinets, but students would leave them on, or they'd set them on their faces and leave them on, so when I'd leave I wouldn't know, and they'd come back, and I got tired of buying batteries. So then I bought these things. Ha! Fixed those students, and now they go around in the lab with their phones, and they turn on the light, and they look in the cabinet, so I don't need those anymore. That was a waste of money. But I'm not bitter. Badness. I know what causes this. There, phew. This is the largest hydroelectric power plant in the U.S. This is in Washington. Grand Coulee Power Station. It's in the Columbia River. It can produce 7,000 megawatts. And is currently being upgraded to 10,000 megawatts. Here are people standing here in what I assume is the giant generator. Leave your pacemaker at the door. Here's the Hoover Dam. You may have heard of it. It's famous. It's big. Hoover Dam generators. Here's going inside. Gigundo giant generators. Here's a staircase with railings, so to give you an idea of the size of these puppies. 17 of them. Each of which can generate up to 133 megawatts. Total capacity is 2,000 megawatts. In the Hoover Dam, a current of 16,000 amps moves from the generator to the transformer. And then they transform it up to the current ramps up to 230,000 amps before being transmitted. Where's it being transmitted to? The grid, yeah. How many amps does it take to kill you? Does anyone have any idea how big a unit is an ampere? It takes 0.2 of an amp to kill you if it goes through your heart. So if you're holding the wire with one hand and stepping in a wet puddle without your sneakers on in the other, so the current goes through your heart, only 0.2 amps. So it's a big unit. If you touch something and the current goes through your hand, you just get a big shock, but it doesn't kill you. But don't try it. Take my word for it. I'm a trained professional. Well, how much of our hydroelectric potential do you think we've already used by building dams and power plants? Do you think we've already used most of it? Hardly any of it? There's lots of room for expansion? About 1/3 or about 1/10? Any guesses?
A.
Huh? A?
It's like a 10. I say 10.
Okay, some people say 1/10. It turns out the answer is about 1/3. But we've done all the cherry picking. We've done all the easy ones. And the hydroelectric potential includes those set-asides like parks and wildlife and so forth. Ohio has 15 hydroelectric stations. This surprised me. I had no idea it was that much, 171 megawatts. Then I looked up, is there any in Columbus? Yes, the O'Shaughnessy Dam up by the zoo produces 5 megawatts of hydroelectricity and a nice reservoir for drinking water. The head is a whopping 18 feet. Okay, well, this is Ohio. And it only runs when there's enough flow, which isn't all the time. So 5 megawatts is the most it can produce. We live in Ohio, get used to it. But hydro's great. It already accounts for a lot of the world energy, but only 20% of our energy, so we should do more of it because it doesn't hurt anything, and it makes great power. But most of the good spots are already used, like Niagara Falls, Columbia River. We have to account for the effect on environment and wildlife. So you can see this is storage capacity. Interesting, they call it storage capacity. You can store energy in a reservoir. So we've talked about how when you flip on the light switch, someone shovels coal into the furnace in Muskingum County. With hydro, if the river's running all the time, you get power all the time. But with a reservoir, you can store the water in the reservoir, and then you can let it out when you need it. So it's a way of storing energy in a sense. But this is storage capacity, millions of acre feet, and this is year from 1880 to 2000. And you can see it's starting to taper off. That tells me the good places are already done. Because if we could do this, why wouldn't we? And these are the reasons that we don't. Okay, so how's the energy budget look so far in the UK? Well, with hydro, the production is still a little bit ahead of the consumption, and next time we're going to talk about light. Do I have an Ohio stack here? No, I do not. Maybe next time I'll have one. Are there any questions? That's as much as I prepared today, so I'm going to let you out a little bit early. Please don't sue me. If you'd like to play with these generators and motors, you may. Otherwise, run and play.